welcome to True Projects. In this video, we are going to explain about the project that is FICformer, a multi-factor fuzzy Bayesian imputation cross former for big data driven agricultural decision support system. So before getting into the execution, first let us understand what is this project about. In today's world, farming isn't just about planting seeds and watering crops, it is becoming much more data driven. Farmers now use technology called Decision Support System, that is DSS, which are smart tools that collect and analyze information from many sources like sensors in the fields, satellites in the sky, and other monitoring devices. So these systems help farmers make better, more informed decisions. For example, they can tell when and how much to water crops, predict how fast crop will grow, or even warn about potential pest problems. By using these insights, farmers can save resources like water and fertilizers and also increase their crop yield. Essentially, these smart systems are making farming more precise, efficient, and sustainable, helping farmers get the best results with less guesswork. So, one of the biggest problem with this smart farming system is that data they collect isn't always complete. Sometimes sensors stop working, signals get lost, or environmental conditions change, which helps gaps or errors in the data. If this incomplete information is used to make predictions, it can lead to mistakes, and the results may not be accurate. Most traditional expect that is Most of the traditional models they expect perfect, complete data, so they struggle where there is uncertainty or missing information. This makes it harder for farmers to trust the system's advice. That's why it is really important to have better ways to handle missing or uncertain data so predictions about crop growth, irrigation, or pest control are reliable and useful. So, to overcome with all such issues, the proposed system is designed to solve the problem of missing or incomplete data in the smart farming. It does this by using a smart prediction framework that combines fuzzy Bayesian imputation module. So it uses fuzzy Bayesian imputation, that is fuzzy logic Bayesian inference and deep learning models. So the system first it takes a model called fuzzy Bayesian data imputation. So the first step in the system is called fuzzy Bayesian data imputation. This part works like a data fixer. It fills in the missing sensor readings. It uses fuzzy logic to deal with the accurate. By doing this, the system turns incomplete, messy data sets into complete and reliable information, which forms a strong foundation for making better predictions and decision about crops. Once the missing data has been filled in the dataset and the dataset is complete, the dataset uses a multi-factor prediction model to make forecasts. So this model looks at multiple factors at the same time like temperature, humidity, and soil moisture, and also considers how these factors change over time. So by analyzing these predictions, that is these relationships together, system can give more accurate and reliable predictions about things like crop growth and yield. In the end, this means farmers and agricultural farmers get better insights, helping them make a smarter decision support system, use resources efficiently, and run more sustainable farms. So, to further improve the performance of this project, here in this project, we are incorporating multiple techniques. So, the original FICformer model was improved by creating a hybrid and stacked deep learning model. This means multiple algorithms are combined to work together, which helps the system to perform better and be more reliable. And moreover, specifically, FICformer was combined with GRU and bidirectional layers. The attention mechanism in FICformer helps the system understand complex relationship between factors like temperature, humidity, and soil conditions, while the GRU and bidirectional layer are good at tracking patterns over time. Together, this makes the predictions more precise and robust, giving farmers better guidance for the decision making. And here we have developed a simple web interface by using Flask framework. So a user-friendly interface has been created by Flask, which is a web framework, and this interface lets users easily input data like sensor reading and receive the predictions directly from the trained models. Moving on to the implementation. To implement this project, here we have followed the steps which are mentioned in the libraries, that is, which are mentioned in the flow of work. So first, we will be loading the necessary Python packages and modules required for data handling, pre-processing, modeling, and visualization. Then comes initializing Spark session. So here we start a Spark session to handle and process large-scale agricultural data efficiently. Then we collect the data, that is, we gather the data related to crop growth, temperature, humidity, soil moisture, and load it into the system for analysis. And we will be doing data pre-processing and missing value identification. After that comes fuzzy Bayesian imputation. So here we will fill in missing sensor data using fuzzy logic and Bayesian inference to ensure the data set is complete and reliable for modeling. Then we do data normalization and splitting where we scale the data to a uniform range using normalization and divide it into training and testing sets for model development. And we will be training the model and evaluating them. And coming to the front end, users, they will be able to use a Flash based web application where they will be able to register login, they will be able to give the sensor data, it will be pre-processed, it will be fed to the trained model, and the trained model will be giving us a prediction. So this is how we have implemented the project. Coming to the algorithms used, so these are the algorithms used in this project. So LSTM is the extension model, existing model, and this model is a proposed model, and these both are the extension models. Moving on to the requirements. To implement this project, basically we need two kinds of requirements, which are hardware and software. In hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3. Front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute it. To execute, open the code folder that contains source code files. So these are the source code files of the project. Let's understand them. In this folder, we have the dataset that we have used. So let's open it. So this is the agricultural data that we have used to train the models for prediction. So here we have temperature, humidity, crop growth. Here we have luminous intensity, and here we have CO2 concentration and total radiation. So here we have total radiation. So this dataset we will be using for training. So this is the test data that we will be using in this project for prediction purpose. And this is the model folder in which we have algorithm information, and this will be loaded into the project code during runtime of the application. This is the static folder in which we have files related to CSS, JavaScript, and Bootstrap files, which are important for this project's visual appeal. And here we have templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here we have two Jupyter Notebook files, which contain a combination of code, graphs, and outputs all in one place. And it allows users to write and execute code in individual cells, making it a popular choice for the data science. And here we have two files, that is for my attention py file, which is the proposed model, and here we have fuzzy Bayesian imputation model. And here we have main.py file. So this file contains information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have Windows BAT file. So instead of executing this project through command line interface, we have created this Windows BAT file. And here we have database file, which is used to store the user information. So this is all about the code folder. Now let's execute. To execute, double click on this run flash.bat file. So here you can see main.py file has been compiled, which will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flash framework will host the application locally at the default address, which is the localhost and the port, unless configured differently. So this is the localhost and this is the port. So copy this local link provided by the Flash framework and paste it into any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. So paste the link here, click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flash framework. So we need to get registered first. So click on register. So first you need to create an account. To create an account, you need to complete registration process where you need to fill in all these details. I have already registered, so I will directly log in. Click on back to login and provide your username and the password. Now click on login. We have logged in successfully and redirected to this prediction page of this project. So you need to do prediction, click on start prediction, or you can click on fast crop. So here you can see upload file, right? So you click on that and select data file and click on predict crop growth. And here we got the prediction. So here you can see prediction has been completed, and this is the test data that we have given. And the predicted crop growth is 24.1894. And here we have confidence for each test data that we have given. So for each case, that is for each case, we have predicted crop growth, and here also we have the confidence growth. So here we have test data, we have predicted growth of 24, and for this we have 15.49. For this one we have 26.6, and for this we have 26.38. Accordingly, for all the values we also have the confidence score. You can even click on download results and you can do the new prediction. So we're done with the prediction. So let's see the data visualization. Click on it. And here we have proposed model performance graph. So this graph is the LSTM load prediction graph. So here on x-axis we have test data, and on y-axis we have growth prediction. So red color is the true growth and green color is the predicted growth. True growth is nothing but it is the actual growth, and green is the model's predicted crop growth. Here if you see, there is lot of variation in the color, so that is why LSTM model is not working. So with this graph you can judge that LSTM model is not working. And this is the proposed FICformer workload prediction graph. So here you can see red color line and the green color line, both of them are almost mixing. So with this, you can understand that they are working well. And here we have all the algorithms performance graphs. So here on x-axis, we have all the models that we have trained, and on y-axis, we have their scores. So this blue color represents MAE, orange color represents RMSE, and green represents RSE. And here we have extension model performance graph. This is the existing model, and this is the proposed model, and this is the extension hybrid former model graph. So here on x-axis we have test data, and on y-axis we have growth prediction. If you observe among both the proposed and extension green line and red line is more submerging than the proposed model. So with this we can understand that the extension model is performing well. Now click on log out. So, in this way, the smart system helps the farmers make better decisions by turning sensor data into reliable predictions about the crop growth. By filling in missing information and analyzing multiple factors together, it gives accurate insights that save time, resources, and effort ultimately, and it makes farmers smarter, easier, and more productive. So, this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.